These are the notes for LT3 in our impulse and collisions unit. And the target says that I can both quantitatively and qualitatively evaluate the importance of safety devices by using the impulse-momentum relationship. Whole lot of big words there. Quantitatively, what that really means is we're actually going to do calculations to get an exact number that shows us, like, why is it by extending time the force goes down. So we'll actually calculate that force. Qualitatively is more just in general, where we can just say, well, airbags, if we can extend the time to stop, the force on the passenger or the driver, whatever, the force goes down. So we're going to get specific when we do the quantitatively. That'll be numbers, and then we'll just qualitatively just be able to evaluate why extending time makes things safer. All right, if you are not in class, then you should click on Moodle and watch the NASCAR video, because some of this stuff that I'm going to put in notes is not going to mean anything to you unless you watch that NASCAR video. So, with this impulse-momentum relationship, the idea behind seat belts, for one, the idea behind the safer barriers that were discussed in the video, the Hans device. Okay, remember that stood for head and neck support. Okay, all of these work on the same principle. Okay, all of them, where if we can increase that time to stop, we will decrease the force on the car, the passenger, the race car driver, whatever. They gave an example in that video. So, let's say that you've got a race car and it's going to have to stop, and let's say in 1/10 of a second. Okay, I'm not even sure what that exactly would feel like, but 1/10 of a second, they said that that driver in that car would experience 80 G's of force. So to think about what that would feel like, take your body weight and multiply it by 80. So you'd have that crushing into you, essentially. Okay, 80 G's of force. But if we could take that same race car and we could slow it down over a longer period of time. So if a race car stops in 2/10 of a second, so we have doubled the time to stop. Doubling the time to stop would cause the force to be cut in half. So then the driver would only experience 40 G's of force. Okay? So this idea of force and time, we know that those are inversely related. If we can make that time go up, that force will go down, and there will be a greater chance of that driver walking away. All right, and that was the gist of the video, and we've already dealt with this a lot in previous targets, so this really isn't anything new. The new part has to do with the calculations. So if you're in class, you have this sheet. There should be a link to this on Moodle. If nothing else, you should be able to just kind of follow along and look under here. All right. So LT3 practice calculations. What you'll see is a picture like this, and what this says, because that's hard to see and it won't let me zoom in, that's an initial velocity. So you have a car hitting a wall at 5 meters per second, and then it's going to rebound, it's going to bounce off at 4. Remember, rebounding is bad, bouncing is bad when we deal with collisions, because that wall essentially has to catch that car and throw it back. So our change in velocity is 5 plus 4. Okay, our change in velocity, when we look at this picture, is 9 meters per second. In case B, we have a car coming towards the wall, hits the wall and just stays there. So this car had a crumple zone, which caused it not to bounce back off. So your change in velocity is 5 plus 0, which is just 5 meters per second. Okay, so we may need that in order to solve some of these problems. On your formula sheet, all of these are essentially saying the same thing. I know it doesn't look that way, but we know that this is change in momentum. We know that I is impulse. In order to calculate impulse, it's force multiplied by time. And that impulse equals a change in momentum. So we could say Ft equals P. That would be the same thing. Where this triangle is at, this is technically correct, but for us, the mass of whatever the object is doesn't change. So you'll also see the triangle in front of the velocity, because for us, I'm not going to have a fender fall off the car and then we have to figure out the change in mass. We won't do that. Okay, so if you wanted to rewrite it like this on your blue sheet, that might be a smart move, since this is the one that you'd want to use at the testing stations. Okay, so I would do that. So pause me if you need to while you take care of that. All right, here we go. We talked about how important units are in here. And so we start to read through these little story problems, and we see that the time of impact is 0.75 seconds. We just start labeling what we know. The force between the car and the wall is 50,000 newtons. Newtons is the unit of force. We're looking for the mass, so that's what we're trying to find out. And then sometimes I'll just say within the story what the change in velocity is, but in this one you need to look at case A. And we already mentioned that if you rebound, you have to add those together, so the change in velocity is 9 meters per second. So you start looking at what you know. We know the force is 50,000. We know the time is 0.75. We know the change in velocity is 9. And we are looking for the mass. That is what we are solving for. Once you make a list of what you know, because one of the biggest struggles people have with this target is I don't know which equation to use. Just look at your sheet and pick the one that you have everything for. Okay, clearly this one won't work for us right now because I didn't give you specifically change in momentum. I didn't specifically give you the impulse, so that's not going to work. Well, this one's closer, but we have a force and a time to deal with, so we're going to deal with this bottom one. All right, so we select our equation, and then you substitute them in. So 50,000 is our force, 0.75 is our time, mass is what we're looking for, so I'm going to leave it as m for now, and the change in velocity is 9. At this point, algebra class takes over. So we're going to multiply the 50,000 and the 0.7. We're going to write it correctly with the number in front of the variable, so 9m. So 50,000, here's what I'm doing. So 50,000 times 0.75 gives us 37,500. And then we need the variable alone. This says to multiply, so we do the opposite to solve. So 37,500 divided by 9, and we get 4,166. It's always round to the 10th, so we need this number, and this 6 says we kick it up. So 4,166.7. Technically, it's kilograms, but all that we would type into Moodle is that. All right, number 2. It says assume the force between the car and the wall in case B is 40,000 newtons, and the car has a mass of 2,000 kilograms. So we start labeling. What do we know? We have a force. We have a mass. We're looking for a time in this case, and we're looking at case B. And in case B, we said the change in velocity is 5. So we have a change in velocity of 5. We have a force of 40,000. We have a mass of 2,000. And we are looking for time. Considering I have these 4 variables, I'm going to use the same equation as I used in the previous one. And so we say Ft is mass change in velocity. You substitute what you know. So we have 40,000. We have time, which is what we're going to solve for. We have the mass, 2,000, change in velocity, 5. So 40,000 t, 5 multiplied by 2,000 gives us 10,000. Divide each side by 40,000. Divide by 40,000. And so 10,000 divided by 40,000 gives us 0.25. we would round that to 0.3 in Moodle, and it's technically in seconds. Okay, so 0.3. Number 3. In a car crash, the change in momentum of the car is 50,000 kilogram meters per second. Change in momentum, that's new. So that's like a triangle P. It takes 2 seconds, that's a time, and we're looking for force. So this time, force is what we're solving for. We have a time of 2 seconds, and we are looking then to figure out the change in momentum. So change in momentum is 50,000. So now the question is what formula? Because if you look back at this old one, I don't know mass, I don't know change in velocity, and so therefore how would I possibly solve for that? Well, you go back to your formula sheet, and we know that impulse, which is the Ft, also equals change in momentum. So you could also write it as this. Okay, that is also true. It's just like I don't have every possible combination on here, but it's the same thing. If I is force over a certain amount of time, that would equal that change in momentum. So maybe you want to add that one also to your formula sheet. All right, so Ft equals change in momentum. So F times 2 equals 50,000. Divide by 2, divide by 2. So our force is going to be 25,000 newtons. So 25,000 is what we type in there. On to the back. In a collision with the floor, a ball has a total change in velocity of 6 meters per second. So we have a change in V. The time of the collision is 0.5 seconds. So we have a time. The mass is 0.25 kilograms. We're looking for force. So that's going to take us back to the one that we used earlier. So Ft is m triangle V, change in velocity. And we substitute. So F 0.5 equals 0.25 and 6. All right, I'm going to move it up over here. So I'm going to have 0.5 F. Then I have to go 0.25 multiplied by 6, which gives us 1.5. Then we divide each side by 0.5, and divided by 0.5, that should be 3. So the force, 3 newtons. Number 5. A cyclist crashes into a tree and has a total change in momentum of 200 kilogram meters per second. Here's our change in momentum. Time, 0.75. Looking for force. Okay, we've done something like this. So I'm looking for force. I have a time of 0.75, and I have a change in momentum of 200. Okay. Well, we know Ft equals change in momentum. So F times 0.75 equals 200. So we're going to go 200 divided by 0.75 to solve this. We get 266.6 repeating, so 266.7. Last but not least, number 6, a 0.5 kilogram coffee mug, kilograms is mass, falls onto the floor. Its change in velocity is 3. Looking for impulse. Impulse is I. This is a little tricky at first because you might think, well, the formula for impulse is force and time. I don't have a force and I don't have a time. Well, we also know that impulse equals change in momentum, and to get change in momentum, it's mass multiplied by a change in velocity. So impulse equals the 0.5 kilograms multiplied by the 3 meters per second, which is the change in velocity. So 0.5 times 3, we should get 1.5. So the impulse is 1.5. Remember, the units are weird. A Newton second Just means that's how much force is applied in a certain amount of time. 1.5 newtons per second. All right. So hopefully you've worked your way through all of those. Now on Moodle, there's an LT3 mandatory practice, because sometimes you just don't know what you do know or don't know until you get to the actual testing station. And for this one, there's no point going to the testing station unless you can do these problems. So you have to complete the LT3 mandatory practice on Moodle. You can take it unlimited times. There's no time limit. Use your formula sheet. Use a calculator. And once you are successful on that, 5 out of 5, LT3 is ready to go. Good luck.